All right, so last time we looked at logarithms, we did 5-4 part 1, which covered basics of logarithms, how you combine them, how you split them, how to take something and change it from exponential form to log form, and the other way. We'll be looking at that again today. All right, so first thing, just kind of using some of our properties of exponents, just to kind of get back in the swing of some of the rules. Okay, it gives us an exponential expression, a to the 2x plus 3y minus z. And they want us to rewrite it just in terms of a to the x, a to the y, and a to the z. Okay, so I want to start by looking at that exponent. Okay, when you add things together in an exponent, what does that mean you had originally? Somebody give me an example. When do you add exponents? And then we'll talk about when you subtract exponents, and that's going to be the second part. Yep?
Okay, so you said when you add exponents?
Yep, what's the rule? When do you add exponents?
When you're multiplying two terms.
Multiplying two terms. So what if I had something like a times x?
Like when you're multiplying two terms with exponents. So it's like if it's a to the second plus x squared.
Times
x squared, excuse me, then it would be ax to the fourth.
Not quite. Ax squared, there wouldn't be anything you could actually do with that. And that's the second part of what I'm looking for someone to add on to what Marina said. So it is when you multiply, but
they have to have the same base.
Right, they have to have the same base. So if you had something like a squared times a squared, then that's a to the fourth. Okay, if they have different bases, you can't do anything with it in terms of adding exponents. All right, so if we've added 2x plus 3y, what would that part have to have been originally? Yep.
A to the 2x times a to the 3y.
Yep. A to the 2x times a to the 3y. And what's the rule when you subtract? When you subtract exponents, yep.
They were divided.
Yeah, when you
so
divide.
it would be divided by a to the z.
Divide by a to the z. Good. Okay, and now the last step, let's look at the denominator. That's already written the way they wanted it. Okay, a to the z, so that's fine. Okay, a to the z. Now, when would you multiply exponents? We have an a to the 2 times x. When does that rule come up? Multiplication of exponents. Yeah?
When, for example, you square a base that's already being squared.
Or it could be any other power. Yeah, when you have a power to a power, so a to the 4th to the 5th, that'd be a to the 20th. All right. So how would you write a to the 2 times x? Yeah.
A to the second to the x.
Yeah, you could do a to the 2nd to the x, or if we write it the way they want it, in terms of a to the x, you square a to the x, you cube a to the y, and you divide it all by a to the z. And that's it. So we've rewritten it in terms of a to the x, a to the y, and a to the z. Any question on that? All right, so just trying to get back in the swing of using our rules of exponents, since it's been a little while. Okay, we looked at this problem once already. We already have the answer to it back in another section. The way we solved it before was with graphing. All right, we would graph an exponential growth curve, we'd graph a horizontal line, and we looked where they crossed. Well, now that we know logarithms, we can solve this algebraically. So we have a town that has an initial population of 50,000, going up at 2.5% a year. I want to know how long will it take to reach 100,000 people? Right, so first thing we have to do is just make sure we remember our exponential growth equation. So in this case, our population as a function of time is equal to, you take your initial amount, times, in parentheses, 1 plus your rate. Anybody remember how the rate has to be written? Be careful, we can't just plug in the rate as a percent. What do we have to change it to? Yeah?
A decimal would be 0.025.
Yep, we're going to have to change that to a decimal. And that's raised to the t. Right, in this case, that's what we're going to solve for. We're going to solve for t. And the reason you're going to need a logarithm is because you're going to solve for a variable that's in the exponent. Anytime you have variables in the exponent, that's when you use logarithms. Okay, what's our initial amount here? 50,000. Okay, as Marina said, my rate is going to be, move that decimal 2 places to the left. We get 0.025. So what's going to be in parentheses once I add 1 to that? Let's do that step all at once. Oh, Andrew?
1.025.
Yeah, 1.025 to the t. And what do we want the population to hit? It's going to equal how much? Yeah.
100,000.
100,000. All right, so first thing we could do to try to start getting t by itself is at least move the 50,000 to the other side. Justin, how would I move the 50,000 to the other side? Yeah, let's just divide by 50,000. And divide by 50,000. And Justin, what does that give me? 100,000 divided by 50,000? 2. Now I have a very simple exponential equation. How do we solve an exponential equation? We have to change it from this form into what form?
So you have to change it from exponential form to logarithmic form?
Yep, so we have to change it to a log. So if we're going to change it to log, start by writing that down.
The base is the same as the base in the log.
So yeah, what was my base up above?
1.25.
Yep, 1.025. And what about my argument and what goes on the other side by itself?
Argument is 2 and t goes on the other side?
Yeah. Okay, so that's our answer. Now, the only problem is we have to know how we can type that in. Do anyone remember how you type that in? Because that's not a log with a base of 10 or e. Well, I showed you something you can do on the TI-84, but if you don't have a TI-84, I'm going to show you a different way you can do it today. But for now, if we don't have a TI-84, then we don't know how to solve that. Right? So we're going to have to look at this again a little bit and maybe come up with a slightly different way to solve this equation. But Andrew, do you remember how to do it on here?
Oh yeah, I go to math and then it's to the thing and then it's down. Log base.
Log base. Yep. So if you have one of these, you can actually type in whatever you want for the base. 1.025 and 2. Right, and it's 28.07 years. Good, it's good you remembered that. Now let's see we don't have that kind of calculator. Okay, let's go back up to that step right there. Instead of changing it to log form, okay, one other thing you're allowed to do, and I think we've done it before, is take the log of each side. So you get log of 2 equals log of 1.025 to the t. Okay, and now we have a rule about exponents when you have them on an argument and a log. you can take that exponent and put it in front. So now you don't have an exponent that's a variable anymore. This becomes t times the log of 1.025. And how would we undo multiplying by log 1.025? Remember, that's just a number. Yeah, you divide by the log of 1.025. So that cancels. And there's another way to get your answer. So if you type in log of 2 divided by log of 1.025 on your calculator, you should get 28.07. And everybody has a button to do it that way. Just use your regular log button. When you type it in, make sure you use parentheses. And we get the same thing. So this might give you a hint at how you type in a log with a different base. Okay? This is actually a formula we're going to learn in a little bit. But it's basically you take the log of your argument, divide by your log of your base. That's how you type something in that has a different base, other than 10 or e. Yep?
The batteries on this are that.
Yeah. Great. So any question on solving that? We'll probably stick with the way on the left once we know the formula. The way on the right takes a little longer, but it's not that much longer. All right, so next thing we're going to do, we're going to try what's called a statistical regression. Okay? In Algebra 1, you did this with a line of fit. Try to find a slope and a y-intercept that fits a line of points. But in this case, the example I have here, does it look like a line would fit that data? Well, no. It's more of a curve, and it looks like more of an exponential curve. So if we can find an exponential curve that fits it, that's called a power function. Okay, and a power function looks something like this. Y equals, and you have to solve for a and m. Just like in slope-intercept form, you've got to solve for m and b. Well, we've got to find two things, a and m. It's y equals ax to the m. Okay, we'll do an example of how you do it by hand, and then I'm going to show you how to do it on the graphing calculator. Okay, so we won't spend a lot of time doing it by hand, because for most examples, I'm just going to let you use a calculator. Okay, let's take a look at this power function. The first thing you have to really know if you're going to use a power function is that the right thing to use? All right? You can graph the data and look at it, but maybe that's a half a parabola. Maybe that's not really a power function. All right? It's hard to tell just sometimes looking at a graph. So we're going to figure out a way to determine if a power function is the right tool to use. Okay? I'm going to start by taking that equation and taking the ln of both sides. So I have natural log of y equals natural log of a x to the m. Now on the right-hand side, does anybody remember how does a product split? You have an argument inside a log that's a product. Splits about, Michael?
You add the log of one part of the other part.
Yeah, it splits as a sum. Right? So we're just going to split the natural log of a plus the natural log of x to the m. And Brandon, what can we do with an exponent on the argument of a log?
You can move it to the outside.
Yeah, we can move it to the front. Put it right on the outside. So I have m natural log x. And I use the commutative property and switch the order. Now for a second, what I'm going to do is cross out all the ln's. Okay, and then I'm going to put them back, but I just want you to look at it if you get rid of all the ln's. Does it kind of look like anything? Yeah?
It looks like the equation of a line.
Yeah, it looks just like the equation of a line. Yeah, it's almost y equals mx plus, we have a different letter, a instead of b. And because it looks like the equation of a line, we can use that idea of something being linear to determine if a power model is the right thing to use here. So in this equation, we say the natural log of y is the linear function of the natural log of x. So we're not saying y is a linear function with x. That's y equals mx plus b. We're saying natural log of y is a linear function with natural log of x. And it's kind of like you have a slope of m and a y-intercept with what's right at the end. Okay, so the way another way to say that is that power model, you can use a power model for the data if and only if natural log of y is a linear function with natural log of x. Right, in our next example, I'll explain how you use that with some data. Right, so to determine if a power model is going to fit that data, first thing you want to do is check, you're going to make a table, right? And you're going to check in that table if it's linear. Okay, what's the table that you're going to make? Well, they're going to give you a table that looks something like that. Table for, there's some x values and some y values. Well, that's good. That's the data that I want to try to model. But to see if a power model fits it, I'm going to make a new table. I'm going to make a table where I take the natural log of every single number there. So I'm going to look at natural log of x and natural log of y. Once I make this table, if it looks linear, okay, when I graph the data in this table, the ln x, ln y table, that's how you know a power model is the right thing to use. So you take all your original data, you take the natural log of everything, and then you look at that table. If it looks like it's a straight line when you draw it, then you know to use a power model. Once you've decided that a power model is the right thing to use, then you have to find your b. I switched to using b because most people are used to seeing it like that when it's at the end, more like a y-intercept. You have to find m. It's kind of like your slope. And then you're going to write your final answer. Right, so we'll go through an example. Okay, so in the example, first thing it says is determine if a power model is appropriate for the data below. Okay. The way we're going to do that, we're going to take the ln of every number in that table. And we'll make a new table right below it. Okay, so let's just start and go through. So natural log of 1 is 0. Natural log of 3 is about 1.1. And again, it doesn't have to be exact. We're just going to look and see if this data would pretty much fall in a straight line. Okay. Natural log of 5 is 1.6. And 8 is about 2.1. Okay, ln of 5 we already have earlier. That was 1.6. All right, 31.2. It's about 3.4. 73.1. It's about 4.3. And the last one is 160. Okay, now everything we're doing right now has nothing to actually do with finding the power model. All this is going to do is tell us whether or not we should even try to find a power model. That's all that this is going to do. Right, let's graph it. All right, so we have 0, 1.6. We've got 1.1, 3.4. 1.6, 4.3. Just try to estimate now the best you can. And 2.1, 5.1. 2.1, 5.1. Okay, does it look like that data falls pretty much in a straight line? Yep. So what that tells us is, okay, go ahead, try to find a power model. That should fit the data pretty well. Okay, now let's actually go through it. You no longer need this lnx, lny table. You're done with it. We've already used it for what we needed. Now we need the original table. Right, just like when you're trying to find slope and y-intercept, you need 2 points. We're going to take 2 points from this table. Right. Let's take 1, 5. Okay, we'll use that one. And 8, 160. Okay, and let's fill them into that equation we had on the other page. lny equals m lnx plus lnb. It's basically like y equals mx plus b if you take out all the ln's. Let's start by solving for b. Okay, now a hint, anytime you have a point that has a 1 in it, I would use it. Because when you take the natural log of 1, we just saw it comes out very nice. It comes out to 0. All right, so let's fill in what we've got. So natural log of 5 equals m times the natural log of 1 plus b, natural log of b. Now at first you kind of look at that and you're like, wait a minute, I got 2 letters there. If you have 2 letters, you can't really solve it. But what did we just say the natural log of 1 is?
0.
And what's 0 times anything? So that whole part disappears. And we basically have our kind of what's the y-intercept. Right, so we know what goes at the very end of the equation. Natural log b is equal to natural log 5, or b is equal to 5, basically. What else do we need besides b? Yep,
M.
we need m. Okay, so now we'll solve for m. You can't solve for m, though, until we have b. But now we have it. B is 5. Okay, this time, I'm going to use a different point. I can't use 1, 5, because if I keep using 1, 5, it's going to cause m times natural log of 1 to always cancel out. I can't have that cancel out if I want to find m. All right, so we're going to have natural log of, now 160 is my y value. Equal to m times natural log of 8 plus ln 5. Any question on that? Now my goal, I'm going to try to get m by itself. So I'm going to bring ln 5 to the other side. And on the left-hand side now we have a subtraction. What would this have been originally before it was changed into subtraction? It would have been what? Yeah, it would have been the natural log of 160 divided by 5. Good.
It's not ln 5?
Well, if we're recombining it all into a single natural log.
Oh, gotcha.
Yep. And now 160 divided by 5, that comes out nice. It's 32. And I want to do one other thing on the right-hand side. I have an m now in front of a natural log. What are you allowed to do with that m? Yeah?
Put it as the power to the 8.
Yep. And now when you have a natural log on each side like that, you can cancel it out. Now we get 32 equals 8 to the m. Now my suggestion here is if you notice 8 and 32, they're both powers of what number? 2. 2 to the 5th is 32. 2 to the what is 8? 2 to the 3rd. Or if now we have our rule power to a power, that's why we went over that earlier. So rewriting it, the bases match. Now you need to make these match. So set 5 equal to 3m and figure out what m is. How would we get m by itself there? Yeah, divide by 3. Okay, so m equals 5/3. Okay, now we can write our final answer. We've done all the hard work. We've got m, we've got b. Final answer. And there's a little bit of simplifying we have to do, but that part will be pretty straightforward. Natural log of y equals m times natural log of x plus, was it ln 5. So in your final answer, you fill in for m and b, just like you do with y equals mx plus b. Never fill in for x and y in the final answer. Right, and I'm going to try to simplify some of this. So I'm going to take the 5/3, put it back as an exponent. And what does addition combine as? Yep.
Multiplication?
Multiplication. So it's 5/3 goes back up as your exponent. I've switched the order a little bit, but it's ln of, let me fix that, 5 x to the 5/3. Combines as multiplication. And what can you do with your ln's on each side? Yeah,
Cancel them out?
you can cancel them out. And now we finally have the equation that models that data. Okay, y equals 5x to the 5/3. All right, so that's the steps of how you go through and you do it by hand. All right, there is quite a bit to do there. You've got to remember your rules for logs, and all kinds of other stuff. So let me show you how you can do it on the calculator. Okay, questions on that? Seem okay? Kind of. If you look back at the steps, it's very mechanical. It's not like writing a proof where you kind of have to think about what to do. You just have to go through a lot of steps here. But there's nothing you have to think about. It would be the same steps every single time. Nothing would ever be different. So it's just remembering all the steps. All right. So what I want to do now is type it in and see if the calculator can confirm what I got. So once you turn it on, go to Stat, go to Edit, and type in your data from the original table. So I've already started typing in some of the data. Finish typing it in. Put your x's in L1 and put your y's in L2. Hey, is there anybody that couldn't get to that screen? So it's 1.5, 331.2, 573.1, and 8160. Everyone have the data typed in? All right. So now once you type everything in, you're going to press Stat again. Go over to Calc. And you're going to keep going down till you find what says Power Regression. Okay, on mine it's choice A. You go down to Power Regression. Now everybody type the X's in L1 and the Y's in L2. If you did that, then you can do pretty much what I'm about to tell you. If you didn't, you'd have to do something else. Okay, if you go to Power Regression, on a TI-83, I think you just have to hit Enter again at this point. On a TI-84, I have to go down and Calculate. Now I can hit Enter. Everybody get an equation, something like that? All right. So now it says A is 4.99999. It's basically 5. That's what we got right there. Now it's saying B was 1.6, bunch of sixes. Let's check. If you divide 5 by 3, do you get 1.6 repeating? Yeah. So it's just giving it to me as a decimal. But that's the power regression, and that's correct. Right, so now if we type in that equation, okay, this part you can just watch. When you graph it, it should go right through all those data points. Okay, what's our smallest x value? We went from 1 to 8. Let's just go 0 to 10. That'll be fine. And y values, we got to go 0 to, say, 200. And again, this part isn't necessary. I'm just going to show you that it's going to go right through those points. And I got to turn my stat plot on. Okay, so let me do two things. Right, so if I turn on one of the stat plots, it's going to use the L1s for x, the L2s for y. Since my line is in blue, let's do the points in red. Do something different. And we found the curve that goes perfectly through those data points. That's called a regression. In Algebra 1, you did it with a line. We just did it with a curve. All right, so from now on, we kind of did it once the hard way. We did it by hand. We can use the calculator to find the regression line. Right? But I wanted you to see how much work the calculator is actually doing for you. It takes a long time to do it by hand. Okay, any questions on that? So there's our final answer. All right, so that finishes up everything we didn't do in 5.4. And 5.5, we're going to look more at graphs. So in the graphs, we're going to do a lot of things we've already done before, like translating up and down, left and right. Okay, that kind of typical transformation stuff. Okay, so here's an example, and I'm finally going to show you how you type something in with a different base. Okay, we already kind of saw it on that population problem. But the idea is if you have to take the log of x base b, x and b can be any positive real numbers that you want. Remember, you can't take the log of 0. That's undefined. So are negatives. Okay, any positive real number you want. Just take the log of the argument, divide by the log of the base. And it turns out it doesn't matter which kind of log you use, whether you use common log or natural log. I would just pick one way and remember it though. All right, so let's say I asked you to find log base 8 of 5. Okay, if you got a TI-84, you can type it in using the log base function. If not, type it in this way. Log 8 divided by log 5. And that's the answer. Now let's say you use natural logs, because I also had that up there. Well, that'll come out the same. Natural log 8, divide by natural log 5. But don't mix them. Either use natural logs or common logs. Don't use both. And then for those that have the 82, log of 5, log of 8 base 5. Okay? So that's how you type in a log with a different base. Any questions on that? Okay, so we're going to graph that. Log base x of 3. Okay, how would I type that in? Because say I didn't have the 84. Type it in the way most people would have to type it in. About Nick? How do I type that in? Using the change of base formula. Okay. Yep. Natural log of?
Natural log x over natural log 3.
Sure. Could I have done it with common log too? Yeah, it would have come out the same. Right, and let's hit graph. We'll start with the standard window and then see. If you have a stat plot on, you can shut that off. Yeah, it's the standard window. Okay, so we talked a little bit about this before, but do logarithms have horizontal asymptotes? No, they look like they go up slower and slower, but they never level off. Okay, and here, remember we talked about what this graph really looks like. Does it stop right where you see it on the screen? No. It just gets very steep, right? So if you try like 0.001, you are at -6, even though we can't see that on the screen. How low will this function keep going? Yep.
Negative infinity.
Yep. And how high?
Infinity.
Yeah. So the range is negative infinity to infinity. Okay, the domain. That's how far left and right it goes. Well, there is a vertical asymptote, okay? And that's going to be the y-axis. The vertical asymptote is at 0. If you try negatives, the function is undefined. Okay? So as long as you pick something that's positive, just barely, it'll work. So what's my domain here?
0 to infinity.
Yep, 0 to infinity. What kind of symbol on 0?
Parentheses.
On infinity?
Yep, parentheses.
Good. That's it. That's the domain and range. Questions on that? Generally, log functions always have a range of negative infinity to infinity. The domain can change depending on if you took that function and flipped it the other way or did a reflection over the x-axis. Okay, it all depends. So the domain can change, but the range not as much. Okay, all your standard transformations apply. What does A do? Oh, Tahina?
Horizontal shift.
Yeah, that's going to be a horizontal shift. How about B? Well, Taylor, do you remember what B does? Everything inside the parentheses, that's all the horizontal stuff.
Horizontal.
That's a horizontal stretch, yeah. And if b was negative, that could also cause a reflection over the, that's going to reflect it horizontally, so it would flip something left to right. C, that's your vertical stretch. And that can also cause something to reflect vertically. In other words, up or down, like over the x-axis. And the last one is D. That's your vertical shift. So there's no change there from every kind of transformation we've done before. A and B do the opposite of what you would expect. Positive would shift it left, negative would shift it right. Bigger numbers make the graph more compressed. Smaller numbers make the graph more stretched for B. C and D do what you would expect. For C, bigger number stretches bigger, smaller number compresses smaller. For D, positive shifts up, negative shifts down. It's exactly the same. All right, so using that information, I want to figure out what the base 3 doesn't really matter that much in terms of transformation. It's more that negative in front of the x. Okay, so what did we just say? What's that negative going to do? It's going to reflect over which axis? And think it's horizontal, so it's going to do some kind of horizontal reflection. Yeah.
It's going to reflect it over the y-axis.
Over the y-axis, right? So to get, bless you. So log base 3 of x, that's like the basic function you start with. That's like the parent function. All right. So to get log base 3 of negative x, take y equals log base 3 of x and reflect it. So reflect over y-axis. Now we just graphed log base 3 of x. Let's imagine we reflected that over the y-axis. What's not going to change, the domain or the range? It's going to go more like this. Yeah?
The range is not going to change.
Yeah, the range is still negative infinity to infinity. Domain. That is going to change. Anyone else think they can give me my new domain? Just picture that being flipped over to the other side. Yeah, go ahead, Josh. So when you say you're bound, always put the smaller number that's further to the left. Yeah, negative infinity to 0. Okay, where's my vertical asymptote this time? Well, the vertical asymptote stayed right where it was. It didn't move. It's still the y-axis, or the line x equals 0. That's it. That's everything they want. Any question on that? Most people find the graphing stuff a little easier than the last section because we've just done so much with graphing with so many kinds of functions. It starts to be more and more of the same. Okay, so how could we sketch log 3 minus x from log x? Well, first of all, I don't even like the way that that's written. Log of 3 minus x. Anybody rewrite that for me in kind of the standard way we normally have it? Yeah?
Natural log of 3 minus x.
What kind of log?
Natural.
I wouldn't switch the kind of log they have because that's going to switch the problem. I would keep the common log, because that's what they have. It's just that argument that I don't like. So what did you say about the argument? Go ahead one more time.
A 3 minus x?
Yeah, I don't like the 3 minus x. How can we fix that?
Negative x plus 3.
Yeah. To me, the two transformations are clearer now. Okay? First thing you would do is shift which way? And how many units? Oh, Orlando?
You would shift 3 units to the left.
Shift left 3 units, and then that negative, we just talked about what that's going to do. That's going to be a reflection. Right? So you're going to do a horizontal reflection. Let me see that.
So I went over the y-axis, right?
Yeah, it's, you know what, maybe that's a better way to write it. Now the book, I'm just looking at what they did. The problem when the book does transformations is they never stick with the same order. Now the book says to first do a reflection over the y-axis and then shift right. Well, if you reflect first, then technically that would work. Because if you do a reflection, then all your transformations, they get reversed. But I don't like to think of it that way. Let's just stick with it this way. So shift left 3 units and then reflect over y-axis.
So in what order would you like us
We should do it that way. Because sometimes just stick with the A, B, C, D. That's why I did those letters that way. Do A, then B, then C, then D. So again, our answer doesn't match up with the book here, but it is correct. Okay, so that's fine. When we have to graph a log function, it's helpful to find the intercepts and where the vertical asymptote would be. Now remember, logarithms only go in one direction, so you might not have a y-intercept. It's possible it doesn't cross the y-axis, but it will always cross the x, because the range goes up and down forever. So we learned that if something's continuous and it goes from negative to positive forever, it's got to go through 0 somewhere. So it'll always have an x-intercept. So your x-intercept is when y is 0. Your y-intercept, that's when x is 0. And to find your vertical asymptote, just set the argument equal to 0. Because whatever value would make the argument 0, that's where the graph starts to become undefined. Or the function is undefined. And if you need more points, just pick a few more x's and graph them. But remember, logarithms only go in one direction, so you have to pick x's that make the argument positive. If you pick x's that make it negative, you're going to get undefined values. Generally, I don't think you need that many points to graph a log function. They all kind of look like that, pretty much. The only difference is if you flipped it or reflected it, but they're all going to have that basic shape. Right, so let's try to sketch that. Log base 2 of 3x plus 5. Okay, just looking at the argument, I already know what to kind of expect. I'm going to be shifting the basic function 5 units to the left. And that 3 is going to compress the graph. Okay, what happens when you compress the log function is it takes something that was more of a smoother curve and it starts to make it a little bit sharper of a curve. Right, so that's kind of the idea of what's going to happen. And after we graph it, then we'll look at the domain, the range, and the vertical asymptote. In fact, I think we're going to find the asymptote first, because that's going to help us graph it. What did I say earlier to set the argument equal to find the vertical asymptote? Let's see.
Set it to 0.
Yeah, set it to 0. So 3x plus 5 equals 0. Here's our vertical asymptote. Okay, let's find x-intercept. X-intercept is when you fill in 0 for y. Okay, so set this entire function equal to 0. 0 equals log base 2, 3x plus 5. Right, how can we solve that? This is an equation that's in log form. Oh, Julia, what could we do with an equation that's in log form?
You can put it in exponential.
Yeah, let's put it in exponential. Good. Right, so 2 is my base, 0 is my exponent, and that's equal to 3x plus 5. Anything to the 0 power gives me 1. And now I'll just finish solving. Minus 5, you're going to get negative 4 equals 3x. Divide by 3, divide by 3. That's my x-intercept. And let's find the y-intercept. Now, y-intercept might not exist. It depends. Right, so let's plug in 0 for x. So y equals log base 2 of, if I fill in a 0, 3 times 0 is 0. 0 plus 5 is just a 5. This will have a y-intercept. Okay, we just need to find it. Okay, and use your change of base formula. If you don't have a TI-84, just type it in like that. Okay, so you can kind of see where we're using a lot of the formulas today. Okay, 2.3. All right, let's make our sketch. So my y-intercept, 2.32. My x-intercept is negative 4/3. That's negative 1.3. Let's graph the vertical asymptote. That was at negative 5/3, so negative 1.6 repeating. Let's do my asymptote in green. And I'd say let's just get one more x value. Let's go out to when x is 10. That's just going to give us an idea of how sharply this is going to curve. Right, so when x is 10, I get, let's see, 10 times 3 is 30, plus 5 is 35. It's log of 35 base 2. And again, you don't have to use 10. I just picked 10 because I like 10. So we get about 5.1. So it's not going up that fast. Okay, and just try to connect that the best you can. So remember, it comes down and it just gets closer and closer to our asymptote. There's a good picture. So our domain is everything from the asymptote to the right. So what was it, negative 5/3? Our range goes up and down forever. Asymptote, we already found that. So I think that's all I want. Any question on that? So there's a typical, that's how you do those kind of graphs. All right. And our last problem we'll look at will be an application. Okay, how many people have heard of the Richter scale before? When you heard an earthquake? Okay. Anybody ever done anything with it? I don't know, in physics, or you ever studied it? No. So this is the formula that the book gives us for the calculation they use to find out what the Richter scale number is for an earthquake. It involves a logarithm. It's got 4 variables in it. Okay, R stands for the magnitude of the earthquake. So when you hear on the news like a magnitude 5.2, that's the R value on the Richter scale. Okay, A is the amplitude of the vertical ground motion in micrometers. Okay, T is the period of the wave in seconds. So when you have an earthquake, just like when you have a sound wave, you can think of a sound wave as a kind of like a graph of sine or cosine. Okay, so we haven't studied a lot about that yet, but you do get kind of a wave in the ground as the earth is moving from the earthquake. And B is a factor that accounts for the weakening of the wave. Right, so that would be like taking into account the kind of ground you have. Is it loose soil? Is it compact soil? Is it granite? You know, what kind of bedrock? A ground, I would think a ground that's very solid, like a rock, that's going to transmit energy better than a ground that's loose and not packed very tightly. I would think loose soil would tend to absorb some of the impact of the earthquake. I could be wrong, but that would be my thought. Right, we're going to use that formula to answer this question. So it says at the early stage of an earthquake, we don't know the exact vertical ground motion, but we'll just say it was A. So at some stage during an earthquake, the vertical ground motion was A. At a later stage, it became 10 times as much. So the ground started moving 10 times as much as it was. Now remember, that's in micrometers. So it's a very, very small movement. But the question is, how much did the intensity change? In other words, what's the difference in the Richter scale number? If the ground starts moving 10 times as much, how much of a change in the Richter scale is that? So we're trying to find a change. What do you generally do when you want to find the change between two things? Like what it was before and what it was now. What do you do with those numbers to find change? Like think about like your grade on a term 1 and then your grade term 2. If you want to know the change in your grade between the terms, what would you do?
Subtraction.
Yeah, you'd subtract. So we're going to use subtraction here. So let's find the measure on the Richter scale at one point minus the measure on the Richter scale at a different point. Right? Let's let this be when the ground motion was 10A, just because that's bigger. Usually when you find a change, if we want to keep it as a positive number, you've got to do bigger minus smaller. And we'll let the time on the R1 be when the ground motion was only A. Right? So now we have to fill that into our formula. So we've got log of, okay, it's A divided by T. Now we're going to assume that everything else stays the same between these two time periods. That the ground was the same kind of soil now and later. The period of the wave stayed the same. Everything's staying the same except A. It's the only thing that's going to change. All right, so A over T plus B. So T is going to be the same. B is going to be the same. What's that numerator going to be? Whoops, I'm sorry, this one was 10a. Because that's what I said earlier, 10a. And the other numerator? Yep,
A.
just a. So you're doing that. What's on the left minus what's on the right. What do I have to do with this minus sign? Yep.
Distribute it.
Yeah, it has to be distributed to the log and then to the b. So we're going to get log 10a divided by t. Now, before I keep writing, does anybody see something that's going to happen here? Yep.
The b's are going to cancel out.
Yeah, you're going to get a plus b, distribute the negative minus b. So the b's cancel out. There's going to be a lot of things that end up canceling out here. That's log of a over t. Okay, any question on that? All right, now let's look at this first part. We have a logarithm that's a quotient. How can we split that up? Yeah,
Subtraction.
as subtraction. Can you tell me what it would be? Log of,
Then A.
yep.
T. Of T.
So it's log of 10a. But now we need a second log because we're going to change it to subtraction.
Minus log of t.
Minus log of t. And now do the same thing here. Now remember, we have a minus sign in front of that, and we're going to be splitting this into two. So there's a minus sign that's distributed again. Log of a minus log of t. Anybody see anything there that is going to cancel out? Yeah, Josh?
Log of t.
Yeah, you're going to have log of 10a minus log t minus log t. So that's a minus log t plus log t. Now that's gone. So we just have log of 10a minus log a. Now every variable here is gone except one, the vertical ground motion. I want to take these two logarithms and put them back together now. Okay? How would you recombine subtraction? As what?
Division.
Division? And what would that be?
That would be log of NA divided by A.
Okay? And what happens there? Log of 10 times a divided by a.
It would just be log of 10.
Yeah, the a's cancel out. And what is the log of 10? In other words, 10, this is a common log, so 10 to what power gives you 10? Yeah, 1. You get a 1. So, the difference in the Richter scale, if the ground motion increases by a factor of 10, is a 1. So when you're talking about like a magnitude 5 versus a magnitude 6, okay, a magnitude 6 earthquake is 10 times more powerful with the ground motion than a magnitude 5. Now, if you were to skip 2 magnitudes, let's say you had a magnitude 5 earthquake and a magnitude 7. Anybody know the difference in the ground motion there, based on what we did? So from a 5 to a 6, it was times 10. From a 6 to a 7, that would be a times 10. So how about from a 5 to a 7? Yeah,
That's 100.
it's 100, right? So you might think, oh, magnitude 5, magnitude 7, you know, they're only 2 numbers away. Well, one of them was 100 times more ground motion than the other. So each Richter scale number is a factor of 10. Okay. Any question on that? All right, so tomorrow I won't see you guys, so I'm going to give you the homework assignment for tonight and tomorrow together. Okay, so this is all due on Wednesday. Okay, so 293 is 35, 36, 43, 44, 46, 48, and 49. And then 301, the section we just did, it's 1, 5, 8 through 11, 16, 17, 23, 25, 28, 32, 42, and 52. All right, and again, that's all due on Wednesday. Okay, when you come in Wednesday, all we're going to do is review that, and that'll be it.